Hello there, friends and neighbors. I want to show you how to compute a quadratic regression. And before we get started, I want to convey the caveat that you will not have enough information to do one of these in real life. It actually is a pretty complicated technique, and it requires a lot of experience and skill to technically do it correctly. The reason I'm teaching it in Pre-Calc 1 is so that we can get an idea of the kinds of things you could do with mathematics, with quadratics and linear models to model real-world behavior. It's extremely useful. Okay, so I'm going to show you real quick how to do this in Excel, but it is beyond the scope of the class. Okay. So percentage of police officers who are women are listed in the table below for various city populations. So for cities between 0 and 9.999 thousand people, we'll use 5 as a single number to represent that interval. They have 8.3% female police officers. For 10 to 24.999 thousand, which will represent as 17.5, they have 7.5% female officers, and so forth. We can copy these data into Excel if we wanted to do it in Excel, and just paste it, then select the two columns, insert, and you insert the scatter plot. There we go. Left click on the scatter plot and add trend line. I can display the equation and also the r squared right there on the chart. R squared is the proportion of variance that's explained from one variable to another, from the input to the output. And then I can choose different types of models. This is a linear, and it's got 97% of the variance accounted for. I could also fit, let's say, an exponential, and it accounts for a little more. I want to get a bad model. A logarithmic doesn't fit well at all. The r squared is 0.64. But the best of them all for this particular data set is a quadratic, a polynomial of second degree. So, and it has 0.99, so 99% of the variance is accounted for with that equation. And that's just a quick demonstration of how it would work. I don't expect you to be able to actually do it. It's just kind of fun to see. These are the coefficients that we get from the regression equation, and I printed them here for you. You'll notice I used 6 decimal places for the leading coefficient, and that should tell you something. Quadratic regression is tricky, and it's very, very sensitive to slight changes in the data. So this equation will change a lot, and again, it takes a lot of experience to be able to do it correctly. Anyway, here are my 3 terms, A, B, and C. This is a quadratic exactly like all the other quadratics we've learned about. Let's look at this scatter plot. I want to point something out. This line is the best possible quadratic that could be fit for this data. It minimizes the squared deviation from each point to the line, but notice that the line itself doesn't actually touch any of the points. So whether it touches points or not is not important. What's important is if I were to take this line away, I would see that same general trend. It looks pretty good. It's a good fit for the data. If I were to remove the line, I could imagine that it would be there. It's the best possible fit for those data. Okay, so now let's answer the question. Is this a good fit for the data? Well, yes, this function is a good model for the data. Here, now I'm given a town of x equals 261.1 thousand people. I'm going to plug that in here. Now I'm going to compute my y, that is the percent of cops, of female police officers there. Y equals a times x squared plus b times x plus c. And that's the prediction. I predict that if you have a town of 261.1 thousand people, it'll have about 15.1% female police. 15.1. Okay, and I can show the answer, and there we go. Now, if I know that a town has 9% police, I want to know about how many people live there. So if I let y be equal to 9, that's a quadratic equation where I'm solving for, I'm setting y equal to some value, and I'm solving for x. So if I let y be 9, I could then solve for x, subtract 9 from both sides of the equation. And this just gets wrapped up into the constant term. It's like having a different value for c. So the equation becomes negative b plus or minus square root b squared times 4 times a times c minus 1 all over 2a. C minus 9. I think I said C minus 9 all over 2a. So let's go ahead and actually compute that. Stick an equal sign in front of it. Every place where I say B, I'm going to click on that cell. And I'm going to do the plus part first, and I'll do the minus part second. 4 times A times C minus 9, 2 times A. And boom, that's a solution. So if it's got 9% female police officers, probably it's got 69.1 thousand people living there. I'll do the same thing for the minus side. So minus square root of all that stuff. What? Negative? You can't have negative population. That's the point. This is where the equation breaks down. That's called an extraneous solution. So I've got negative 269.1, negative 269.1, comma, then the upper one, 69.1. And that's the answer. Lastly, what does this mean? Well, it means that 9% of police officers are women in cities with populations of about negative 269.1 thousand. That means nothing. But it is also true at real values of 69.1 thousand people. And that's what it means. Ta-da!